Okay, so we've been starting a new topic, linear maps. And these are maps between vector spaces. So if I had a map F for vector space V to a vector space W, then I say this, the first one. Oh, let me put the overhead on. Okay, so this first space V is called the domain. And the second space, it should be coming up shortly. And the second space, W, is called the codomain. And so the action works like this. For what we mean by a map is for every V that's inside the domain, there is a W such that W equals F of V. So you take any vector and you put it in an F, the map produces a W, okay? So this is called the image of V, under F. Every map will produce a different image. Okay, so that's the basic terminology that now, to be a map, it has to be that you can't have the situation. F not a map if you have a V and you had two W's, right? Two images. So you could imagine this in two ways. You could say, okay, well, since if you pick two for every two vectors v1, v2, right? If f of v1, that would be w1, is not equal to f of v2, right? So you can't have this. This is like this is ruled out. Okay, so the point is, if you choose any two domain vectors, then they both have images, f of v1, f of v2, and if those two happen to be different, then that has to imply that v1 is not equal to v2, because if it was, you'd have this bad situation in which you had one v going to two image vectors. Okay, but this is got two negatives in it. So what happens? So that you can also say, well, if you can turn it around, and this is logically equivalent, if v1 was equal to v2, like if you happen to choose a v1 and v2 and they happen to be the same, then that means that f of v1 has to equal f of v2. So those are two different ways of saying f is really a map. This is the defining condition. Of map between vector spaces, okay? And so this it basically says informally that you choose a vector v and you get a single vector out. You can't get two out. It's like a determination. It's sort of the whole idea of dependency. So so the whole concept here is one of dependency. So, for example, like a function could, like one function could be, like they oftentimes occur in the real world. If you had like one of these, you've probably driven over or seen one of these black strips that the traffic department will put down on the road, and they will count traffic. And you could say, well, the number of cars that goes over in a particular hour is a function of the time of day. So you choose a particular hour, say 11 o'clock to 12 o'clock at night on one day. Well, you can't have like two different numbers of cars going over the road at that point. There's either going to be 20 cars or 23 cars, but you can't have 20 cars and 23 cars. That's like, so that this dependence, you're looking for a connection between time of day and the number of cars that goes over it. So you choose a time of day, and a given hour, there's going to be a certain number of cars that go over, and that's a dependency relation, so that defines a map. So that's what they're looking at. So they sort of correlations between different things you can measure. So that's the idea that a map captures, is a dependency relationship. And so that's why functions appear all over science, because that's the core thing you're looking for. You're looking for to measure two different quantities. Like you measure the height of a building and how long it takes for a bowling ball to fall from the height of the building to the ground. Well, hopefully no one's going to do that these days, but that's the kind of thing you're looking for. Okay, so now, so then we saw that maps have two kinds of properties. There can be maps can be one-to-one or onto, or what they can be one or the other, or both, or neither. They're completely independent properties of given maps. These two things, one-to-one and onto. And so what does one-to-one mean? Well, it means it's the same kind of thing here, that if I choose for all, say, vectors v1 and v2, if v1 is not equal to v2, then it has to be the case, to be one-to-one, that f of v1 is not equal to f of v2. And then no, it has to be the other way around. It has to be that if v1 is equal to v2, no, it's, okay, sorry about that. If v1 is not equal to v2, if they're different, then these have to be different. Okay, now if you compare this with this one up here, this is this one says, okay, if the two images of v1 and v2 are different, the vectors have to be different, right? You're ruling out this. But this is sort of the reverse. What you're ruling out is if you're ruling out if v1 is not equal to v2, that they go to the same w. So it's sort of like, let's see, it's sort of like two different in the domain go to the same in the codomain. This is the opposite of the thing up here, the thing at the top, that the well-defined condition says you can't have one vector in the domain going to two in the codomain. One-to-one says you can't have two different vectors in a domain. This is okay for a map, but it's not okay to be one-to-one. So it says if v1 is not equal to v2, then f of v1 can't be equal to f of v2, because here, this w would equal f of v1 equals f of v2. So this condition rules out this situation. And we can turn it around, and at the same time, if f of v1 happens to equal f of v2, that's got to imply that v1 equals v2. So you can sort of say, well, if I do have the situation where I have f of v1 equaling to v2, then it had to be the case that v1 is equal to v2. Again, either one of these conditions rules out this. And these two, and you can see sort of here, this is v1, v2 on the left, and the images on the right. This is the images on the left. So they're sort of like, you just sort of flip the things that are there. So they're connected in a certain way. And this is going to be important when we look at inverse maps, because the only inverse maps you can have are ones that are going to be one-to-one. Because an inverse map sort of switches the domain and codomain. So this will be, it's sort of useful to sort of get the general pattern of these sort of formal definitions. Okay, well, this gives you the idea of one-to-oneness. And I just review, this will be the last time. So I haven't put the videos up, but I'll put those up shortly. And then, okay, the other property is onto. And this says for every, if a map is onto, for every W that's in the codomain, there exists a V in the domain such that F of V equals W. So you can take any vector in the codomain, and there's got to be a vector in the domain that maps to it. That means that sort of nothing gets left out. Okay, so it's sort of like what you can't have is a W here with no V over here that maps to it. There's got to be a V that maps to any W, because that's onto it. It means you sort of like you've targeted the entire codomain. Okay, so it's easier to see those concepts when you have finite sets, but then vector spaces have infinite numbers of vectors, so it's harder to see visually. We can sort of draw arrow diagrams between particular vectors, but we can't draw the whole picture. Now, if you have both of those, if that is, if a map is 1-to-1 and onto, then it is called an iso. Well, it's called a correspondence. Getting ahead of myself. It's called a correspondence. Now, these concepts apply to all maps, not just vector spaces. But this is true. This was true in calculus when you had, for example, you had a real function like f of x equaling, say, x squared. So if I was to draw a graph of that, like in the xy plane, so a function is a map. And if you draw a graph of this, you draw it like this, right? So if you treated f as a map from the real numbers to the real numbers, the domain and codomain, then you can see this map here is not onto, right? Because the domain is every vector here, but every real number here, but you never get any negative numbers, right? So it's not onto. Unlike g of x equals 2x, which let's see, just so I can. So if I then drew, like this would go something like this, right? I just wanted to show so that this is G and this is F. This is onto, right? Because I put in a positive. For any y value, I'm going to get an x value, right? So no matter what I have for the y value here, I'm going to have an x value that maps to it. And you can see that if whatever y value I divide it by 2, and that's going to be the x value. Now, however, and also G is also 1-to-1, right? But F is not. No, F is 1-to-1. No, F is not 1-to-1. Sorry about that. F is not 1-to-1 because the point is that I could have, say, here 1 and -1 both go to 1, right? So as a result, I've got 2 domain elements go to 1 codomain element. And you could have some kind of test where you'd take the graph of the function, look at a horizontal line, and it should only intersect the graph once. And if it intersects it twice, it's not 1-to-1. Whereas here you can see wait, sorry about this. I'm speaking a little bit too quickly. G is also 1-to-1. Yeah, I've said it correctly. F is not 1-to-1 because you can see that, and you can see it. Okay, so this is just trying to say that you're familiar with these concepts, or that they have a realization in terms of ordinary maps, which you call functions between R and R. And your focus here has been on, for these maps, they're always R to R, real numbers to real numbers. And so you're interested in different kinds of functions you have. And here we're going to be interested in very simple functions. They're always going to be linear. We're not going to have analogs of x squared. So we're more interested in the different spaces between the maps. So it's a little bit, our interest is a little bit different because we're looking at like different domains and codomains, but all the maps are linear. So this map here is like linear, and this is not linear. Okay. Shruti.
So how would F be onto, or
F is not onto because you can't get negative numbers. Okay. In other words, that if F is onto, I should be able to choose -1 and solve if
that's not 1 to 1 or onto.
Yes, it's not one. If F were 1 to 1, then there should be an x, that x squared was -1. And if F was 1 to 1, then -1 squared would not equal, if not, well, this is rather, sorry, the other way around. If F were onto, then it'd have to be an x that produced -1. If F that doesn't seem grammatically correct. If F was onto, then there would be an x that maps to -1. If F was 1 to 1, then 1 squared would not equal -1 squared, because this is two different values that go to the same target. And the same thing, 2 and -2. So x squared is not 1 to 1, neither onto, whereas G is both 1 to 1 and onto. And there's other maps that you could have that would well, let's see. I'm not sure what exactly you can have in these ones. Because if it's 1 to 1, you might not be able to have, well, you can definitely have a map that's 1 to 1 and not onto. But I don't know if you can have one that's onto and not. Anyway, go ahead.
So by that logic, would that mean that anything that was or any equation or any function that was squared can't be 1 to 1? Because if you square it, then it will.
Yeah. If any map that's what you'd say is an even function, you can sort of say, if I change x to -x and I get the same value, that's clearly not going to be 1 to 1, because I have two values going. Now, whether or not it's, for example, so therefore x cubed would be a function. X cubed would define a function that would end up being both. I think 1 to 1 and onto, because you get negative numbers and you get it's sort of the graph of x cubed. X cubed would be another, h of x equals x cubed would be something, curvy that was like 1. So you can have, this map is 1 to 1 and onto, but not linear, right? So what we're going to be interested in is linear maps. So the linear property is also a kind of structure preserving property.
I'm sorry, so H is 1 to 1, but not onto.
What? Excuse me. Oh, this one is not linear. This is H is 1 to 1 and onto, but it's not linear. And because it's got the x cubed in it. Okay, so we're getting interested in linear maps. And let me